So we will see that if we do integration, we'll get exactly the same result that we developed previously in 2D. Okay, and this is a physical result stating that I can determine for any point A, the angular momentum about this point is physically what? It's the moment of vector mg about A plus the angular momentum about G. Okay? And this is reasonable because we know that when we reduce to G, okay? So when I reduce at G, I have mvg as linear momentum, and I have the angular momentum is vector hg, okay? So now, if I want to compute the angular momentum about any arbitrary point A, so I need to displace my system from G to A. From statics, you know that if I displace a vector from one point to the other, I should consider its moment about this point. So the general formula for arbitrary point A is R between RG relative to A, which is vector AG, vectorial MVG. So this term will represent the moment of vector MVG about A, plus AG, which is a free vector. So I should account for it when I consider the angular momentum at point A. So it's exactly the same result we have developed before in 2D analysis. Okay. And in particular, if you consider, if you want a fixed point, if you have rotation about fixed axis, okay, as we have seen before, we can demonstrate that. We'll see in next slides. So you have the velocity will be 0. So you will see that you can develop, in this case, a simple formula for rotation about fixed axis. And also we'll develop together a general formula for angular momentum about G. So in case you have general plane motion, you can deduce angular momentum about any point from this formula, while in case you have rotation about fixed axis, or you can use the general form, or you can use a particular equation that we'll see together, which is exactly very similar to what we have seen in 2D motion. Okay, but now how to compute if you want these equations in Cartesian coordinates, and how to get the components of the angular momentum hx, hy, and hz. All you have to do is to develop the formula, and is a formula for a general, if you want, xyz axis, is integral over m rho vectorial omega vectorial rho dm. So this is the general form about any axis, if you want x, y, and z, having arbitrary orientation. So all you have to do then is to perform the integral. And if you develop your integral, you will see that you can find a final expression for angular momentum about x, angular momentum about y, and angular momentum about z. So you can evaluate these angular momentums according to these relations. Okay, so here also you need the tensor. As you can see, you need the tensor of inertia, because to compute angular momentum about axis of arbitrary orientation x, y, z, you need to develop first what is the expression of the tensor of inertia about these axes, and what is the components of omega in x, y, and z. And of course, you have the right to directly use these formulas. You know that it's an open book material, so you can directly use these equations. All you have to do is to specify your axis of interest. So you need to do, whenever you say, I want to do angular momentum about G, this means what? Hg is a vector. Okay, so because it's a vector, it will have 3 components, one about x, one about y, one about z. So when you say, I want to calculate angular momentum about point G, you need to take x, y, z axis passing by G, and you need to evaluate the inertia tensor about this axis. And once you get angular momentum about G, you can deduce the angular momentum about any other axis, if you want any point. because once you get vector hg, you can deduce h about any other point A using this formula. يعني HA is simply AG vectorial MVG plus HG. So to evaluate HG, you can use the following method. You do the expansion and you calculate HXG, HYG, HZG. Once you have this vector, you can deduce the angular momentum about any other vector. Okay, but as you can see, of course, if you can select X, Y, Z in a way to have products of inertia equal to zero, this will simplify things a lot for you. يعني, you need to try to have simple calculations. So if you select X, Y, Z axis in a way to have principal axis for your rigid body, you will cancel out these terms and you will have a simple way to calculate your angular momentum. So then Hx will be Ixx omega x, Hy will be Iyy omega y, and Hz will be Izz omega z. So in case X, Y, Z coordinate axes are oriented such as they become the principal axis of inertia for the body at that point, we can simplify calculations since the products of inertia will be equal to zero. And in this case, if the principal moments about X, Y, Z are represented as Ix, Iy, Iz, we can say that Hx is Ix omega x, Hy is Iy omega y, and Hz is Iz omega z. And now, as usual, okay, you can apply both the principle of linear impulse and momentum and the principle of angular impulse and momentum in order to solve problems. So you are familiar with these principles. The only thing that is new here is that instead of applying them in 2D motion, you will apply them to 3D motion, which is, so this will make the calculation of your angular momentum more challenging, okay? But as formulas, it's the same principles. Okay. So you can see that this chapter, if you want, this chapter is a revision of a lot of concepts that we developed before, but instead of applying them in 2D, we'll apply them in 3D. Okay. So now we defined how to calculate angular momentum in 3D. We'll move to how to calculate kinetic energy in 3D. So for kinetic energy, also same method. To find the total kinetic energy of a rigid body, we need to integrate kinetic energy over the body. Okay. And for each particle is characterized by a certain velocity vi. And you know that the elementary kinetic energy is half mi vi squared. Now, in 3D, we deal with vectors. Because we deal with vectors, whenever we want to perform integration, we'll try to transform this to a vector form. And you know that vi square, vi magnitude square can be written as vi vector dot product vi vector. Okay? So when you perform the integration, you can replace vi by vxi plus vyj plus vzk, and then you can perform, if you want, the integration of your kinetic energy, because you know that each velocity vi vector is related to a certain point. And if you know the velocity at one point of your body, you can deduce the velocity at any point by saying that vi is va plus omega vectorial rho a, which is the distance from A to particle I. Okay? So now, if you perform integration of this formula, okay, and you develop it in XYZ frame, you can demonstrate that. So here these are mathematical demonstration. Okay, so in case you are interested into how we found the formula, you can go over them. But in the exam, you can of course directly apply your result. Okay. So if you do the development and if you apply this formula for particular points, you can come up with the following cases. So if I have rotation about fixed point, then VA is 0. So we can prove that in this case, the kinetic energy can be computed simply as half omega, which is the total angular velocity vector, dot product of the angular momentum about point O. Okay? And in case O is fixed, as we have seen before, you can say that angular momentum about O is equal to IO dot, so so it's related to IO times omega vector. It's the tensor of inertia IO, okay, times omega vector. So in case you have principal, you select X, Y, Z in a way to have principal axis of rotation, so no product of inertia, then when you do IO times omega, you will get that the kinetic energy is half Ix omega X square plus half Iy omega Y square plus half Iz omega Z square. Okay, while if you don't have X, Y, Z if you don't select appropriately the axis, or you are not able to find your principal axis, then the formula will be much more complex. Okay, so that's why we try always to select X, Y, Z in a way to be principal axis of inertia to simplify the computation of angular momentum and the computation of kinetic energy. And in case if you want to use point G, you can use a general form, which is the kinetic energy is half mvg square plus half omega dot product hg vector. Okay, so in case if you want you don't have a fixed point, you have a general form, and you want to find the kinetic energy, let's say in general plane motion, all you have to do is to find the velocity of your center of mass, and you need to compute omega vector, and you need to compute your angular momentum vector, and then you can just do omega dot product hg. And in case you select appropriately, as we said, x, y, z in a way to be principal axis of rotation, then you can write that the kinetic energy is just half Ix omega x square plus half Iy omega y square plus half Iz omega z square. Now, the principle of work and energy is exactly the same as before, but just now the way of computing the kinetic energy is different because it's in 3D. But as principle, it's exactly same. Yani we do kinetic energy at state 1 plus sum of work of forces between 1 and 2 is equal to the kinetic energy at state 2. Let us practice on this using some examples. So first, the following rod has a weight of 25 Newton per meter. Determine its angular velocity just after the end A falls onto the hook at point E. The hook provides a permanent connection for the rod due to the spring lock mechanism. Just after striking the hook, the rod is falling downward with a speed Vg1 equals to 3 meters per second. Okay, so now in this problem, what do we have? We have a rod formed by 3 parts. Okay, it's initially at rest, and then it will rotate, and it will be in contact with E. Okay, then what they want us to do is to find the angular velocity omega at state 2 just after the end A falls onto the hook at E. okay? So we need to find what is the value of omega 2, knowing that it started, so this is the initial position. This is position 1. Okay.
دكتور هي عم تبرم ولا شو؟ ولا هي وقعت بس شو صار فيها؟
لا هي لحظة ما وقعت لأنه خلينا نتأكد. I think إنه first هلا the given is not very clear بس I think إنه أول شيء كأنه عم بيقولوا إنه عملت translation بالأول. Let me check. يلا let us read again the given. Sorry, 1 second. Okay. So the rod has a weight of 25 Newton per meter. Determine its angular velocity just after the end A falls onto the hook at E. يعني what will happen is that this will fall down and it will be in contact. يعني حتكون هيك. Okay. يعني it was first in this position. It will fall down once وقت وصلت على هيدي البوزيشن. يعني وقت وصلت على point A يعطونا انه the rod is falling downward with a speed VG1 of 3 meters per second. يعني the velocity here VG1 is equal to 3 meters. So they gave us the velocity of point G just لما البوينت A صار على البوينت S. And after this يعني بس دقت فيه بس دقت بpoint S. Let me check where is E. So now once it's in contact with S صارت عم تعمل rotation about E. اوكي لانه قالوا لنا انه after يعني اول شيء كانت it's translating وصلت على S with a downward speed VG1 equals to 3 meters per second. But once it reached S they said انه كأنه صار عنا يعني permanent contact بين A و S. يعني كأنه صار rotation about fixed point. So now the hook will provide a permanent connection for the rod due to its spring lock mechanism. So now what it will in this case after this it will do rotation about the hook. Okay. يعني initially the rod was translating and we have a speed VG1 given, and after this once it's in contact with the hook it will do rotation about the axis of the hook. Okay, this is the idea of the problem and we need to solve for the angular velocity. يعني هلا صار عنا إذا بدكم تحولت translation ل rotation, and since we have rotation about the axis of the hook يعني it's rotating about this axis, about x-axis. Okay, then we can apply conservation of angular momentum before and after. We can apply إذا بدكم before and after الcollision الconcept of conservation of angular momentum in collision. انتم بتتذكروا انه whenever we have a collision between two bodies, okay, we can apply إذا كانوا external forces non-impulsive we can apply conservation of angular momentum. هلا here they didn't give us any يعني they didn't give us delta t the time of collision, so we can consider انه delta t is really small. Okay, and since the weight is a non-impulsive force, so we can consider that we can apply conservation of angular momentum about point A. Okay, so here we can say that during delta t, impulsive force F is acting at the hook at A, but since we are applying the angular momentum about axis passing by A, okay, then we can consider that we have conservation of angular momentum because the only impulsive forces here, impulsive force is passing by A, and since A, if you want, is the force is passing by A, when you do moment about A, this moment will be equal to 0. And the other force acting on the system is the weight. And since delta T is really small, we can consider that the weight is a non-impulsive force. Okay, so we can apply conservation of angular momentum about point A. Now we need to evaluate the angular momentum at state 1 and at state 2. Okay, so first, let us consider the angular momentum at state 1. At state 1, what do we have? The rod was doing translation. So we just have vector mvg1. Okay, and to compute the angular momentum of g about A, so we can say that HA at state 1 is only due to translational component. You don't have already omega 1 is 0. Okay, what is your general formula? Your general formula is HA vector at state 1 is equal to moment of vector mvg about A. So it's AG factorial mvg okay, plus the angular momentum about G. Okay, but since initially omega is 0, since initially you don't have an angular velocity, omega 1 was 0. So initial angular momentum about G is 0. Okay, since the angular momentum is IG omega. And here you have that omega is 0. So this term will cancel out at state 1. So at state 1, you just have the moment of mvg1 about point A. So they gave you the velocity of point G, and you have a vector position RGA. You can do the vectorial product. So if you go back to our figure, okay, you can just say that I can find coordinates of vector AG. So if we look at our figure, coordinates, if I take A as the origin of X, Y, Z, so coordinates of point G are along X 0.15.
along y 0.15 ما هيك؟
sorry, along Y. Along Y 0.15. Along X, it's minus 0.2. So minus 0.2 in X plus 0.15 in Y and about if you consider Z coordinate, it's they are in same level, okay, A and G, so 0. Okay, so now these are the coordinates of point G. So all we have to do is AG vectorial. The vector is VG1 is downward. So VG1 is equal to minus 3 K. Okay. So now I can evaluate the angular momentum at point A for state 1 as AG vectorial M VG1 since A is the origin, so AG vector is minus 0.2 I plus 0.15 J vectorial. The mass is given of the system. They said that the rod has a weight of 25 Newton per meter. So since they gave the weight per unit length, all we have to do is to consider the total length of the rod. And we have This is 0.3 meters, 0.2 plus 0.1. So we have 0.3 plus 0.3 plus 0.3, it's in total 0.9 meters. So we do 25 times 0.9. We get the weight. And since we need the mass, all we have to do is divide by G. We divide by G. Okay. So we get the mass of the rod. And we do, so I will take M outside. It's a constant. Factorial minus 3K. Okay. So I just have to do expansion. We know that I vectorial K is minus J and J vectorial K is plus I. So we can get the angular momentum about A at state 1. Okay. Now, second step is to evaluate the angular momentum at state 2. So as we said, at state 2, how we can evaluate the angular momentum? We should apply the general equation, which is the moment of vector MVG about the point at state 2, okay, plus the angular momentum about G at state 2. But now, as we discussed together, when it is in contact with the hook, it will do rotation, okay? And when you do rotation, you can express, you can still, if you want, all you have to do is to relate the velocity of a G. You need to get velocity of G at state 2. To get the velocity of G at state 2, you need to know what is the type of motion. And since we said that we have rotation, okay? So point G will rotate about the hook. And if you go to your figure, what will happen now? Since your rod is rotating about the hook, so we are sure that it's doing rotation about point A, okay? So we need to evaluate the value of VG2 and we need to evaluate HG2. Now, what is the general formula for HG2? First, we have seen that we need to select an appropriate frame XYZ. So we can take XYZ in a way to have a product of inertia equal to 0. And as you can see, if you just take this system, you have two planes of symmetry. And if you take XYZ passing by G in this way, you can say that both are, you have XZ is a plane of symmetry, and also XY is a plane of symmetry. So I can say that the three products of inertia in this system are equal to 0. So since these three products of inertia are equal to 0, I can simply say that HG at state 2 is Ix prime omega xi plus Iy prime omega yj plus Iz prime omega zk. Okay? And in this way, I can replace Hg2 by its expression in my formula. Now, what about the relation between velocity? As we said, we need to determine the velocity of G at state 2. So to determine velocity of G at state 2, we need to apply, if you want, relations. We need to relate the velocity of G to other points. So what do we do in general? We say, let me relate the velocity of point G to the point that is fixed. I know that the hook has a velocity of 0. I know that point G is doing rotation about point A. So I can say simply that VG2 vector can be calculated as omega vector vectorial AG. Okay? In this way, instead of having 6 unknowns, which are, if you replace in the angular momentum relation, you have VG as unknown, VG2 as unknown, and HG2 as unknown. But HG2 was determined function of omega x, omega y, omega z. So it is equal to, as we said, it's equal to Ix prime omega x plus Iy prime omega y plus iz prime. This is along I, this is along J, and this is along K. Because we selected the system, x prime, y prime, z prime, okay, in a way to have the product of inertia equal to 0. So we are able to evaluate the angular momentum function of omega x, omega y, omega z. Now, what about Vg at state 2? The velocity of point G at state 2 can be decomposed in 3D into 3 components: Vg2x in I plus Vg2y in J plus Vg2z in K. And here you have 6 unknowns: Vg2x, Vg2y, Vg2z, and omega x, omega y, omega z. And since you have conservation of angular momentum, you have a vectorial equation in 3D. And a vectorial equation in 3D can give you 3 equations, and you can only solve for 3 unknowns. So you need to reduce your number of unknowns. This can be done by relating Vg2x, Vg2y, Vg2z with omega x, omega y, omega z. And since you have now a rotation about a fixed point, you can relate the velocities of the fixed point, which is 0. So you can relate VA to VG by saying that for a rigid body, what is the general relation between any 2 points? You can say that I can write that VG is equal to VA plus omega vectorial AG. Okay, so if you do so, you can find, when you write this equation, you can relate the velocity of point G to your components omega x, omega y, omega z. Okay, so here in this problem, we just have to write the relation. So when you expand, you will get that Vg2 is function of omega x and omega y. Okay, so you will be able to replace your velocity vector, and here Vg2 is only along K because of what we have here. Yani, from the previous analysis, when you replace in your system, you can demonstrate, when you replace in x, y, and z, 3 equations, okay, you have that from the third equation, you can conclude that you have a omega z equal to 0, okay? So you just have then 2 components of angular velocity to determine, omega x and omega y. But because in this system of equations, you have more than one unknown, and you have Vg2 x, y, z, but here, because they did, if you want, analysis, and they said that Vg2 should be perpendicular to AG, okay? So if you go to your figure, look at your figure. Just after collision, this is AG. AG is in which plane? In the horizontal plane. So Vg, so you can do some analysis to simplify your calculation. Vg at state 2 is perpendicular to AG. And since AG is horizontal, so Vg at state 2 will only have one component along K. And you can already say from your analysis that Vx is 0 and Vy is 0. If you didn't pay attention for this, it's not a problem. When you write the relation between A and G, you will see this. Let us do it. And if you didn't pay attention that Vg2 is only along that, you'll say, let me relate Vg to point A. So I have Vg 2x in I plus Vg2 y in J plus Vg2z in K equals to VA, but VA is 0, okay, because A is fixed. So 0 plus omega vectorial AG. Omega has three components, omega X in I plus omega Y in J. But from the previous system, okay, we know that omega Z is 0. So we can just replace omega Z directly by 0. Okay. Plus
دكتور ليه حطيت الأكس equal لزيرو بس؟
لأنه مش الأكس equal لزيرو، هيدي V of A. مش أنت you are relating velocity of G to velocity
أوكي.
of A.
Okay, I thought you're replacing the values of VG2X
No,
وهيك
no,
أنت عم
no.
تحط two equations equal
Yes,
لبعضهم.
yes. عم
أوكي.
بكتب إنه عم بعمل الريليشن إنه VG at state 2 is equal to VA, which is the center of rotation إذا بدك, plus omega at state 2 vectorial AG. Okay. So let us suppose
Okay.
you didn't solve yet the system and you didn't know that omega Z is 0. You can add it. So plus omega Z. Okay. And all of these are at state 2, omega X2, omega Y2, and omega Z2. Vectorial AG. So for vector AG, we have already determined the coordinate. Okay. So for AG vector, شو كان عنا 1 second. These are the coordinates of AG. It's minus 0, 2I plus 0.15 J. So minus 0.2 I plus 0.15 J. Okay, so let us do the expansion. We can say that this is equal to, first, I dot I, 0. I dot J, sorry, I vectorial J is K. So we have plus 0.15 omega X2 K. We are done with the first expansion. J vectorial I, it's a minus K, and we already have a minus, so plus 0.2 omega Y2 K. J vectorial J, 0. Finally, we have the last term. We have K vectorial I plus J, and we have minus, so minus 0.2 omega 2Z in J, and K vectorial J is minus I, so minus